So the derivative of a composite function. So this is the first part. So we're going to do a bit of review on composite functions. So given two functions, f of x and g of x, the composite function f of g is defined by f of g is equal to f of g of x, is read as f follows g, or the composition of f and g. Sometimes we refer to f of x as the outer of major function and g of x as the inner or minor function. So we're going to go over some examples to tell you exactly what that means. So f of g, okay, when we have f of g, it is written as f and the inner function g of x. So we know g of x is going to be x plus 1. So we're going to get f of x plus 1. Okay, and because x plus 1 is contained within f, as you can see with f of x, we have a cube up here, which means that f of g of x is equal to x plus 1 cubed. And now same thing with g of f. We can write it as g of f of x. I know that my f of x is x cubed. So now I have to figure out g of x cubed. So what that means is wherever I see an x in g of x, I'm going to plug in x cubed, okay? So because I only have one variable in x plus 1, I sub that in with x cubed. So I get x cubed plus 1. So again, f of g of x, because g of x is x plus 1, which means I can write it as f of x plus 1, which now we read it as wherever I see x in f of x, I'm going to sub it with x plus 1, which is why we get x plus 1 all cubed. Okay, do you guys understand this concept? I know it's just like two brief explanations, but hopefully you guys were cool with that explanation. So I'll put it into a more practical way. So we're finding f of g of 4, okay? So first of all, we need to calculate what g of 4 is. So that would be step 1. So if I calculate g of 4, what value does it give me? What is g at 4? So remember, g of x is x plus 1. So what would g at 4 be? 5. Okay, so when you plug it in with numbers, it becomes easier to understand. So now I have to find f at 5. Okay, we know f of x is equal to x cubed. So wherever I see x, I'm going to plug in 5 for f of x, which means that I get 5 cubed. So what is 5 cubed? What does that give me? $125. With numbers, it becomes easier to understand the composite function because it basically gives you a visual in terms of, finding, evaluating g of x and f of x at different x values. So with that said, this is going to lead us into talking about the chain rule in function notation. So talking about the chain rule and derivatives. So if I move down a bit, so this is what the chain rule is. So the chain rule in function notation is if f of x and g of x are differentiable, then the derivative of the composite function, h of x is equal to f of g of x, is the derivative of h of x is equal to the derivative of f multiplied by g of x which is then multiplied by the derivative of g of x. So, which basically means that the derivative of a composite function is the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function. And I'll get into some examples so that you guys are not confused about this. So the easiest thing to do when it comes to this is to split it up into f of x and g of x. So we're going to get into an example in the next page. This lets me change. Okay. So in example 2, we want to differentiate h of x, which is equal to 5 minus 2x to the 6 times 4, by first decomposing the function and then performing the chain rule. We want to verify our answer using the power of a function rule. So we have our whole function, which is h of x, is equal to 5 minus 2x to the 6 to the power of 4. So now I need to come up with an f of x, and I also need to come up with a g of x. So my function f of x, because we have this exponent 4 out here, we can say that f of x is equal to x to the power of 4, and g of x can be 5 minus 2x squared, or 2x to the 6. So I'm going to write it in terms of a composite function so that you guys understand why f of x would be x to the 4, and why g of x would be 5 to the negative 5 minus 2x to the 6. So remember, we have f of g of x, that is what the chain rule tells us, and we can write it as f of g of x. So I know that my g of x is 5 minus 2x to the 6. Now wherever I see x in f of x, so for example here, I'm going to sub in my expression 5 minus 2x to the 6, and in turn we get 5 minus 2x to the 6, all to the power of 4. Okay, now in chain rule, we need the derivative of both f of x and g of x. So what would the derivative of x to the power of 4 be? For x squared, or 4x cubed. And what is the derivative of g of x? Negative 12x to the 5. Perfect. So now we can use our chain rule, which states that the derivative of h of x is equal to the derivative of f, where g of x is contained in, multiplied by the derivative of g of x. So the derivative of f of x, we said, was 4x cubed, times the derivative of g of x, which is negative 12x to the 5. But because g of x is contained in the derivative of f prime of x, what do I need to sub in for my x? Remember, we're talking about composite functions. F prime of g of x. What would I need to sub in for my x? Or for my g of x, sorry. So because we have f prime of g of x, that means I'm going to sub in, thank you Priyanshu, my function 5 minus 2x to the 6 for x and my derivative. So I get 4 times 5 minus 2x to the 6 and that would be multiplied by negative 12x to the power of 5. And now I can just easily simplify, which means that my derivative ends up being negative 12x5 times 4. So I'm going to multiply these two. Gives me negative 48 x to the power of 5 times 5 minus 2 x to the 6 all to the power of 3. Is everyone fine with example number 2? Okay, I know composite functions can be a tad confusing. So we'll do one that actually has values in it. All right. So when you guys see it with numbers actually inputted, it becomes easier to understand. Okay, so as you can see, number 3, we don't have a function, but we have a composite function. So we have, suppose if f at 3 is positive 4, and the derivative of f of 3 is equal to negative 1, and the derivative of f of 6 is equal to 5, and g of 3 is equal to 6, and the derivative of g at 3 is equal to 2, we want to find the derivative of f of g when it is evaluated at 3. So we know that f of g of x gives us h of x. Okay, that we know. What this question is telling us is what is the value of the derivative of h when x is equal to 3. That is what we have to find. So we know based off chain law that the derivative of h of x is equal to the derivative of f of g of x times the derivative of g of x. Okay? So we have to evaluate for x is equal to 3. Okay? So that's what essentially we have to find. So we have to find the derivative of f when g of x is 3, multiplied by the derivative of g at 3. So now it becomes a matter of looking at the values that we have. So you have f prime. Can someone tell me what g at 3 gives us? 6. So now we're going to get f prime at 6 multiplied by the derivative of g at 3. So who can tell me what the derivative of f at 6 gives us? Five. And what is the derivative of g when x is equal to 3? 2. So what's 5 times 2? Anyone? 5 times 2? 10. which means that my derivative of h when x is 3 is going to be 10. So this is a way of just using the chain rule in terms of composite functions where you're given certain values where f and g of x are evaluated at certain x values. Is everybody okay with this example? We just use the definition of chain rule to help us find the derivative of h of x. Okay. Now we're going to be talking about the chain rule and Leibniz notation. So basically, this is where we have our u statements. So if y is a function of u and u is a function of x, then y is a composite function and dy over dx is equal to dy over du times du over dx, provided that dy over du and du over dx exists, which means that the derivatives of those functions have to be real. Okay, if they're not, then we cannot use this rule. So we have example 4. So we have if y is equal to 2u to the 4 plus 3u squared, and u is equal to root x plus x, we want to find dy over dx at x is equal to 1. So based off our definition, we know that dy over dx is equal to dy over du times du over dx. All right, so we're going to focus on our y is equal to 2u to the 4 plus 3u squared. So this can be written as dy over du because we have y and u in the same algebraic function. So which means that I can just use my product rule and find the derivative of 2u to the 4 plus 3u squared. So what would my dy over du be for 2u to the 4 plus 3u squared? What would my derivative of that be? Eight u3 plus 6u, thank you, Mohammed. It's going to be 8u cubed plus 6u. And now we have u and x, so I can have du over dx. So remember, you can also write this as x to the 1/2 plus x. So what would the derivative of x to the 1/2 plus x be? Can somebody else give me the derivative of that? Okay, we have 1/2 x to the negative 1/2 plus 1. Perfect. Now we can use our, Leibniz notation for our chain rule. So we have the rule dy over dx is equal dy over du times du over dx. Which means that I can take my derivatives of both and just multiply them together. So I get 8u cubed plus 6u times 1/2 x to the negative 1/2 plus 1. Okay, so we want to find out that x is equal to 1. Great, we have x over here. However, we have u on both of these sides. So what do I substitute in for u? Can anyone give me a hint as to what we need to do? And it has something to do with one of the functions that are given to us. So what do we have to do with that 1 and square root x plus x? What do I have to do? So what I'm going to do is I'm going to sub in x for my function u. So I have u is equal to root x plus x, which is equal to root of 1 plus 1, which is equal to 1 plus 1, which is equal to 2, which means that wherever I see u, I can plug in the number 2. So what I'm left with is 8 times 2 cubed plus 6 times 2 times 1/2 times 1 to the power of negative 1/2 plus 1. So when I simplify my first bracket, I get 64 plus 12 multiplied by 1/2 plus 1. So I get 76 times 3 over 2. So when I simplify 76 multiplied by 3 over 2, what do I get as my answer? 114. So how do you guys feel about this example? Does everyone feel good with this example or a bit uneasy? Okay, Anna's the only one who says it's good. Okay, so you guys like it better than just chain rule in general. Luckily, example 5 has nothing to do with the chain rule, to be completely honest with you. It's just to see if you guys remember to find the derivative. So the last one is determine the equation of the tangent line in the standard form to the curve f of x is equal to 1 over 2 times the square root of 3 minus x when x is equal to negative 1. So what would be the first thing I would do in this case, or we would do in this case? Remember, we don't like stuff in the denominator, so what would we rather do? Remember, always think about the square root function as a power of 1/2. Yep, so we can write this as f of x is equal to 1 over 2 times 3 minus x to the 1/2. And now what I can do is just bring this up and have the exponent be a negative 1/2 as I bring it up. So I can be left with 1 over 2 times 3 minus x to the negative 1/2. Now it becomes easier for you guys to find the derivative of this. So how would we find the derivative of 1/2 times 3 minus x to the negative 1/2? It has something to do with the power of a product rule for derivatives. So how would I be able to find the derivative of this guy? So remember, the power of a product for a derivative is I take my exponent and multiply it by my coefficient. So negative 1 over 2 times 1 over 2 gives me negative 1 over 4 times 3 minus x. And remember, I have to subtract 1 from my original exponent. So I get negative 1 over half minus 1, which gives me negative 3 over 2. And now I can multiply that by the derivative of what's contained inside the bracket. So what is the derivative of 3 minus x? What would that derivative be? Negative 1. Perfect. So now I can multiply negative 1 over 4 by negative 1. So I'm left with 1 over 4 times 3 minus x to the power of negative 3 over 2. Now, all I have to do is basically just bring my exponent down to the bottom, and it becomes positive, and which means I can solve my derivative so much more easier now. And because we're trying to find it at x is equal to 1, I have to find the derivative of f at 1. So now all I need to do is sub in negative 1, for my x value. So I get 1 over 4 times 3 minus negative 1, all to the power of 3 over 2, which means I get 1 over 4 times 4 to the power of 3 over 2. And when we use our calculator, I get 1 over 4 times 8, which gives me 1 over 32. So now, by finding my derivative, I now know that the slope of my tangent at x is equal to negative 1. So remember, guys, when you find your derivative, you're finding the slope at your tangent at a certain x value. So this means that the slope of my tangent at x is equal to negative 1 is going to be 1 over 32. And now I have to find an equation in standard form. So what I have to do is I need to find my y value. So I'm going to sub in negative 1 to my original equation. So I get f at negative 1 is equal to 1 over 2 times 3 minus negative 1, which is equal to 1 over 2 times square root of 4, which is equal to 1 over 4. So I have my x value at negative 1 and my y value of 1 over 4. So now I can use my standard notation. Y minus y1 is equal to m times x minus x1, which means I get y minus 1 over 4 is equal to 1 over 32, bracket x plus 1. And now what I can do is just open up the bracket. And to get rid of the fractions, what do I multiply both sides by? To get rid of my fraction, what would I multiply both sides by? What's my biggest denominator? 32. So I multiply both sides by 32. So I'm left with 32y minus 8 is equal to x plus 1. And I get 0 is equal to x minus 32y plus 9. So that would be my standard equation of the tangent line. Okay? So we have one more lesson to do. We'll do it after.